Welcome to The Explainer. I am absolutely thrilled you're here today because, well, we are going on a serious journey. We're going to completely break down the internal workings of a computer. We're starting all the way down at those microscopic bits and logic gates and building right up to the macroscopic operating system. It is a fascinating ride, so let's just get right into it.
You know, Ernest Renan once noted that the simplest schoolboy is now familiar with facts for which Archimedes would have sacrificed his life. And honestly, it is so easy to take our magical devices for granted, right? Every single day, we carry around these little glass boxes in our pockets that perform billions of calculations a second, usually without giving it a second thought. So today, we're demystifying exactly how they do that, unpacking facts that would have literally blown the minds of the ancients.
Okay, so here's the blueprint of the digital city we're about to build today. First, the language of computers. Second, transistors and logic gates. Third, the brain, which is the CPU. Fourth, the memory hierarchy. And finally, number 5, the OS manager.
All right, Section 1, the language of computers, speaking in ones and zeros. So let's explore how computers actually comprehend information at the lowest possible level. But before we even touch on modern silicon, history is totally full of surprises. Just like archaeologists discovering that fierce Viking warriors actually wore red woolly socks, they also found something pretty incredible near Greece, the Antikythera calculator. This was a sophisticated gear mechanism dating all the way back to 2200 BC. It proves that humans have literally always sought to automate math. But, to reach the speeds we need today, mechanical gears just weren't going to cut it. We needed electricity and a way simpler way to count. Enter the bit. Back in the late 1940s, a statistician named John Tukey realized that saying binary digit over and over again was, well, a bit of a mouthful. So he just coined the word bit to describe that basic 0 or 1 state. Because our electronic circuits can easily detect two distinct voltage levels, basically power on or power off, this two-state system turned out to be perfectly suited for computing.
And this brilliantly illustrates how we can use a place value system with a base of 2 to count. In our everyday decimal system, we use powers of 10, right? But in binary, we use powers of 2, 1s, 2s, 4s, 8s, and so on. So for example, 1100 in binary translates perfectly to a 12 in decimal. You just add the 8 and the 4 together. Simple as that. By just using longer strings of these bits, we can represent literally any number.
Moving on to Section 2, Transistors and Logic Gates, the city's building blocks.
Let's move up a layer to see how those abstract ones and zeros actually map onto physical, microscopic hardware switches. We call those transistors. And those tiny transistors are grouped together into electronic circuits called logic gates. The really fundamental ones are the AND gate, where the output is 1 only if both inputs are 1. Then there's the OR gate, where the output is 1 if at least one input is 1. And finally, the NOT gate, which is basically just a flipper. The output is the exact opposite of the input. Now here's the crazy part. By combining just these 3 simple gates, a computer can perform any and all calculations. They essentially create the digital roads of our city's data path.
Which brings us to Section 3, the brain, the CPU.
So how do we actually combine those tiny logic gates? Well, we use them to build the central processing unit. This is the ultimate traffic controller of our digital city. Now, to handle everything we ask our computers to do today, modern CPUs rarely work alone. They use multiple cores. Having multiple cores to handle different tasks simultaneously is exactly like having several chefs in a kitchen instead of just one stressed-out chef trying to cook a massive feast all by themselves. It's what lets you listen to music while rendering a video without your whole system just freezing up.
But what are those chefs actually doing in there? Basically, they're running a highly repetitive 4-step cycle. Fetch, which is grabbing an instruction from memory, decode, translating that binary data so the machine actually understands it, execute, which is performing the math or logic operation itself, and store, saving the result. I really want to emphasize this. That precise 4-step cycle is happening billions of times a second, often at 3 gigahertz or even higher, inside your device right now, just to process this very information.
All right, Section 4, the memory hierarchy, the city's archives. Let's step back for a second to see exactly where our busy CPU chefs are getting their recipes. Enter the concept of memory. We basically have 2 main types. Think of RAM, or random access memory, as the city's public library. It is incredibly fast, and books are constantly being borrowed and returned. But it is volatile. When the power goes off, the library is completely emptied. ROM, on the other hand, read-only memory, is more like a historical archive. It's non-volatile, meaning the data survives without power, holding on to things that never change. So the absolutely crucial takeaway here is that distinction. RAM handles temporary working data while the power is on, whereas ROM holds permanent foundational instructions like your device's firmware.
But here's the thing. Even with RAM, CPUs are so unbelievably fast, they can actually end up just waiting around for data to arrive. So, to bridge that speed gap, we use cache. This is a lightning-fast storage built right next to the CPU to hold frequently used data and cut down on those wait times. But on the other end of the spectrum, what happens when the RAM public library fills up completely? Well, that's when the OS uses virtual memory. It essentially borrows space from your slower hard disk to create the illusion of endless RAM, cleverly swapping data in and out behind the scenes.
And that takes us to Section 5, the Operating System Manager, bringing the city to life. Now we're transitioning up to the macroscopic software layer that orchestrates all of this otherwise lifeless hardware. And here's a question I really want you to ponder based on what we've covered so far. We know the CPU is actually quite naive, right? It's merely executing one single line of machine code at a time in that fetch-execute loop. So how does it not get stuck? How does it actually manage to run Spotify, a web browser, and a demanding game all at the exact same time? Well, the secret to this multitasking is surprisingly simple. The answer to why a CPU doesn't get stuck is exactly the same reason the band Coldplay got so popular. Clocks. Or, okay, more accurately, hardware timers. These timers rapidly and repeatedly interrupt the CPU, triggering state machines within the operating system to pause the current task and switch to the next one. This switching happens so blisteringly fast that it creates this perfectly seamless illusion of parallel multitasking.
Essentially, the operating system acts as our city manager to coordinate all this traffic, using very specific scheduling strategies to allocate that CPU time fairly. For example, round robin is preemptive and gives each process a strict time slice, which is perfect for time-sharing systems. Then you have first come, first served, which is exactly what it sounds like, a simple, non-preemptive queue that just runs tasks in the order they arrive. And finally, priority scheduling ensures that highly critical real-time tasks get to jump right to the very front of the line.
But the OS doesn't just schedule things, it protects the whole system. It enforces rules by using processor modes, which are often called rings. Standard apps, like your web browser or a game, are strictly restricted to user mode, also known as Ring 3. They are simply not trusted with direct access to memory or hardware, period. If they need something, they absolutely must request help from the all-powerful kernel mode, or Ring 0. That is where the core of the operating system operates with absolute, unquestioned authority. To see how this all builds together, just think about when you move your mouse or when an app in user mode needs to open a file. It can't just take the file. Instead, it triggers an interrupt or a syscall, like the int0x80 instruction on Linux. This acts as a massive signal, forcing the CPU to pause its current user mode task, switch safely over into kernel mode, and hand control to the OS so it can process the request securely.
We have mapped out an incredible digital city today. We built it from microscopic logic gates, layered it with memory hierarchies, and set up the strict government using the operating system. But before we wrap up, I want to leave you with a slightly provocative thought. If all of our modern software completely relies on these rigid legacy architectures to function, what is computing actually going to look like when we finally replace the silicon transistor? I mean, are we moving to quantum bits? Or maybe even biological computers? Thank you so much for joining me today to explore the truly beautiful architecture of the computer. Stay focused, stay curious, and I will see you in the next explainer.